we'll talk about an example of a real paper published in Neurology by a bunch of people from Columbia. The topic is association between supplemental nutritional assistance program use, SNAP use, and memory decline. Findings from the Health and Retirement Study. We'll just go over the abstract. So, studies on the effect of the Supplemental Nutrition Assistance Program, SNAP, on the cognitive health of older adults are scarce. We sought to examine the associations between these two things. So the background is just no one's looked at these two variables before. We'll look at them. Here are the methods. They took people who were aged 50 and up and eligible for SNAP in 1996. I guess not everyone who's eligible signs up. They determined eligibility using federal criteria, which I guess could be ascertained using other variables that are collected in the survey, income, stuff like that, number of people in the household. Participants also self-reported whether they use SNAP. So in each wave, they're asked about what types of federal assistance they use, and SNAP is one of the things. And then memory function was assessed every 2 years, every wave from 1996 through 2016, using a composite score to account for pre-existing differences in characteristics between SNAP users and non-users. So in other words, to adjust for confounding. We modeled the probability of SNAP use using demographic and health covariates. So those are the confounders, and they fit like a logistic regression model for probability of treatment, and use that to adjust, which is what we're going to learn how to do today. Then they did something slightly fancy. So instead of just taking, let's say, the composite score 10 years out as their outcome, they fit this model for the trajectory, and they took like a summary of the trajectory that's output by this model as the outcome. But for all intents and purposes, let's just say they looked at the memory score 10 years out, or change in memory score. Using inverse probability weighting to adjust for confounding, they estimated the effect of SNAP use on memory decline. Here are their results. Of the 3,555 SNAP-eligible participants, only 16% were SNAP users at baseline. At baseline, SNAP users had lower socioeconomic status and a greater number of chronic conditions than non-users. So they were different. There were confounders to adjust for. And they're also more likely to be lost to follow-up, which means that there could be informative censoring, which is another thing to adjust for. Their IP-weighted models suggested that SNAP users had worse memory score at baseline, but slower rates of memory decline compared with non-users. And they say that the results were slightly stronger from this alternative form of confounding adjustment, which also uses propensity scores, called propensity score matching. But in other words, our findings suggest that SNAP users had about 2 fewer years of cognitive aging over a 10-year period compared with non-users. So I would have dinged them if this was a submission in the class for using an ongoing treatment at baseline. If this was not a study of new users, a lot of the things that they adjusted for, presumably, so not the demographic things, which would precede SNAP initiation, but presumably a bunch of the health variables could have been post-treatment variables. I think that's a drawback. I'm not sure if they discuss it in the paper. So now we'll do a little bit of review of what we've already done for logistic regression. I'll also go over in a little bit more depth how to assess performance of a prediction or classification model using logistic regression. And then we'll move on to causal inference using logistic regression. Okay, so what have we done? We talked about how the whole idea behind logistic regression is to wrap a linear regression inside this logistic function so that it bounds the estimates between 0 and 1, because probabilities are between 0 and 1. We talked about just how to fit the model using maximum likelihood. We mostly don't think about the technicalities when we're doing logistic regression or interpreting it, but we went over that. Then we talked about some examples of using logistic regression for description and for prediction and classification. We looked at interpretations of coefficients and ways of summarizing the model using plots. We looked at predictive average. That's just a single number, but we also looked at those summary plots of how predictions change with covariates. And we also, in all of these cases, use the model to make predictions for like particular cases of interest, like particular values of the covariates. So then we also talked about model diagnostics and assessment. We talked about binned residual plots to look for lack of fit, and calibration plots to see how closely the predicted probabilities from the model match actual frequencies. And then error rates and ROC curves to measure how good the model is. A key point that I didn't really stress last time is that if you're using like a calibration plot to compare two models to each other, you should assess calibration on a holdout test set that you didn't actually fit the model on, or compute it in a cross-validated way. The key point is that an overfit model or a complicated model will tend to be better calibrated if you assess calibration on the same data that you fit the model to. That's calibration, like how accurate are your probability estimates. Then there's also discrimination, which is like how well does your model enable you to make guesses about whether the outcome is 1 or 0. So in the well example, we gave this example of setting a probability threshold of 0.5, and whenever the predicted probability of switching is greater than 0.5, you would guess switch, and if it's less than 0.5, you'd guess not switch. And you can look at this thing called a confusion matrix, which just counts the number of times that you guess 1 and it is 1, you guess 1 and it is 0, you guess 0 and it's 1, you guess 0 and it is 0. The confusion matrix will depend very strongly on what the probability threshold is. If the probability threshold is very high, then you're only going to guess 1 when your predicted probability of it being 1 is extremely high. So typically you're going to have a higher specificity if your probability threshold is very high, meaning you're not going to be guessing that it's 1 a lot when it's actually 0, because you're only guessing that it's 1 when you're really confident that it's 1. On the other hand, you're probably going to be guessing that it's 0 a lot when it's actually 1. So your sensitivity is going to be really low. You're not going to be picking up the true positives if your probability threshold is really high. In general, as you increase the probability threshold, your sensitivity goes down, but your specificity goes up. The ones you pick are likely to be real, but you're going to miss a lot of real ones. The ROC curve plots sensitivity against specificity for a range of probability thresholds. And ideally, you'd have sensitivity equals 1, you'd get all the real cases, and also specificity equals 1, right? The upper left-hand corner is where you really want to be. And for any given level of specificity, you want to have as high a level of sensitivity as possible. So given your specificity level, you want to guess 1 for as many reals as you can. You want to maximize the area under this curve. The AUC is a commonly used overall measure of discrimination for the classifier. So it has this kind of interesting interpretation that if you're presented with a random pair of observations where one has y equals 1 and the other has y equals 0, the AUC is actually the probability that your model assigned a higher probability that the one that was actually 1 was 1 than that the one that was actually 0 is 1. If you think of it not in terms of a probability, but just like a predictive score, it's the probability that it gives a higher predictive score to the one that's 1 than the one that's 0. So in that sense, it's saying, forget about calibration, forget about interpreting the output as a probability. How useful does it do at discriminating between the ones and the zeros? What proportion of the time that you're given a random 1 and a random 0 do you give the higher predictive score to the 1? That's just another property that you might want your model to have. And it's somewhat orthogonal to calibration. You can have a lot of discrimination power, a lot of power to discriminate between the ones and the zeros without being well calibrated at all. And you can be perfectly calibrated and have no power to discriminate between ones and zeros. So in that sense, they're untethered from each other, but you would like a good model that takes into account informative covariates should be both. This is another thing that you really want to assess if you're going to use it to compare models on pulled out data that you didn't use to fit the model. Because if you use the same data to assess the model that you use to fit the model, more complicated models are just always going to do better. And so that could lead to preferring an overfit model, which wouldn't generalize well, which is bad. From lecture 1, we gave this summary of the types of stuff that you could do with regression in general. I think we went over everything except extrapolation for linear regression, but we'll do that later in the class. So we talked about how you could do prediction, prognosis, what's going to happen, classification, what likely happened, description, which variables are associated with the outcome and how strongly. We've done these 3 for logistic regression. And what remains now is causal inference and extrapolation, which are actually closely related. We'll just do causal inference. Extrapolation is going from in-sample properties to properties in a larger population. So like correcting for non-response in surveys. We didn't do that with linear regression yet, but we will. But of course, we did spend tons of time on causal inference with linear regression, and we haven't for logistic regression yet. So that's what we're about to do. Logistic regression for causal inference via inverse probability weighting. You can read about this in What If on pages 20 through 24 and in chapter 12. Okay, so this is also from a slide from lecture 1 where I was explaining how oftentimes regression is not really like an end in itself, but it's a cog in a machine, right? You fit a regression and that's just part of a broader algorithm or goal with standardization. There was one step, which was fitting a regression for the outcome given the treatment and the covariates. But then there was also the step of setting everyone's treatment values, predicting their outcome, and taking the average. That was like the broader algorithm to get the thing you cared about, which was the average of what if everyone had done treatment. It's the same with logistic regression for causal inference using inverse probability of treatment weighting. In this scenario, we care about the same thing. We want to know the expected outcome had everyone taken a certain value of treatment. And to get at that, you fit a logistic regression model for the probability of treatment given covariates, and you weight everyone who actually took the treatment that you're interested in by 1 over that probability. So we'll go into this idea in a lot more depth right now. Here's an example. On the left-hand side, let's just focus on this tree right now. Suppose this is a tree that describes your data set. So 0.4, 40% of your sample has L equals 0. 60% has L equals 1. Of the people with L equals 0, half have A equals 0 and half have A equals 1. And let's say that's 4 and 4. Of the people with A equals 0 and L equals 0, 75% have Y equals 0 and 25% have Y equals 1. So 3 have Y equals 0 and 1 have Y equals 1. So these numbers at the end, so like the 3, this is the number of people with L equals 0, A equals 0, Y equals 0. The 1 over here is the number of people with L equals 0, A equals 0, Y equals 1. So if we were going to do like an unadjusted comparison to see what's the effect of treatment on probability that y equals 1. What we could do is just look at all the a equals 0 branches and all the a equals 1 branches and compare. So, well, first let's look at the a equals 1 branches. Here's 1. You have 3 y equals 0s and 1 y equals 1 in this a equals 1 branch. And in this a equals 1 branch, you have 6 y equals 1s and 3 y equals 0. Adding these together, 7/13, right? 6 plus 1 over 6 plus 1 plus 3. 7/13. You have 13 total people with a equals 1, and 7 of them have y equals 1. 7/13 of the people in this data set with a equals 1 had y equals 1. And you can do the same thing with the a equals 0 people. One of these a equals 0 people had y equals 1, and 2 of these a equals 0 people had y equals 1. And altogether, there are 7, 3 plus 1 plus 2, a equals 0 people. So 3/7 of the a equals 0 people had y equals 1. So the unadjusted estimate, if you take the difference between these two rates, is 0.11. Now, let's look within levels of L. Forget about assuming there's exchangeability, but let's just look within levels of L. So within L equals 0, if you compare the a equals 0 people to the a equals 1 people, it's 3-1, 3-1. No difference in the rate. No effect of treatment in L equals 0. If you look at the L equals 1 people, 1, 2, 3, 6. 2/3 of the subjects had y equals 1 in the treated and the untreated in the L equals 1 group. So no effect. The effect is 0 in both strata, in both levels of L. The unadjusted effect within L levels is 0. If you assume exchangeability and you do the standardization thing, you'd get that the effect is 0, right? The effect in each level of L is equal to 0, so the overall effect is 0. That's just adjusting for confounding, the usual standardization way. Now let's talk about how to do the same thing, adjust for confounding using inverse probability weighting, just like you can using standardization. Let's move over to this tree over here. This should say untreated, and this one's treated. We're saying, what if everyone were untreated here? So we're going to move all of the a equals 1 people from this tree to the a equals 0 branch. And under exchangeability, their proportion of cases, the proportion of y equals 1s should be the same as observed in the untreated group when we move them over there. So since it's 3-1 and there are 4 of these people, we assume that the new 4 people who we add to these 4 to make 8 total people have the same outcome distribution as the untreated, as these people did. So it would just be now 6 and 2. And then there would be no one who's treated, right? Because everyone's untreated. And now let's see what happens in the L equals 1 branch. So we're moving these 9 people who were treated into the untreated branch. Under exchangeability, these people's outcome rate would be the same as the untreated if they were untreated. And this is a scenario where actually there is 0 effect. The 6 and the 3 are the same as you'd expect from 9 people who are untreated. Even if the effect were non-zero, if we want to say what would happen if you just up the number of people from 3 to 12 and keep the rate the same, you'd get 4 and 8, right? 1/3 of the 3 had an event, 2/3 of the 3 had an event. So 2/3 of the 12, when you add the extra 9 people, should have an event. So it should be 8-4. If everyone were untreated, we'd have 10 events out of 20 total subjects. So now let's do the same thing. Try to figure out what would happen if everyone were treated. We have in the treated group here, 1/4 of people have the outcome. And if we take a new 4 people on board to the treated group, 1/4 of them should have the outcome. So it would become 6 and 2, because 2 is 1/4 of 8. Similarly, if we take the 3 untreated people on board to the treated people here, 2/3 of the untreated people should have the outcome because 2/3 of the treated people had the outcome. And this would become 8 and 4 instead of 6 and 3. We're adding 3 and we're making 2 of the 3 have the outcome. So again, you would have 10, 2 plus 8 of the population out of 20 total having the outcome. So the rate, if everyone were treated, would be 10 out of 20, 1/2, and the rate if no one were treated would be 1/2. So we get that the effect is 0 by going through this process of just taking the people who were similar based on their covariates but received a different treatment, assuming that they would have been the same as the people who received the treatment that you're interested in, adding together their outcomes, assuming that they'd have the same rate of the outcome, and then just taking the average at the end. What are we really doing when we're going through that process? You're taking all of the people who actually followed the treatment of interest. So let's say the what if everyone were treated case, you're taking everyone who actually was treated, you're multiplying their outcome by 1 over the probability that they were treated. So here it's like 0.5. So we're saying if these people had also been treated, we should just double this. It should just be as if there are 2 of these guys. And similarly here, there are 9 of these people. We're saying, what if there were 12? We're saying 1 over 3/4, right? 4/3 times 6 and 3 gets you 8 and 4. To add on the 25% of people to the 75%, you just multiply by 4/3 these outcomes, assuming that their outcomes would be the same. So each time what you're doing is you're multiplying everybody's outcomes so that they represent themselves and people who are similar to them, who have the same L, but who got a different treatment. That's what inverse probability weighting does, is it enables people to represent themselves and the people who are similar to them, but who got the other treatment. And that's how you then address the question of what if everyone got the treatment that you're interested in. This is obviously a very toy example, just meant to build the intuition for why inverse probability weighting would adjust for confounding. It's because the causal question is, what if everyone took treatment? Really, people with certain confounding or values of confounders were more likely to take treatment. And you want to know what if everyone did. What you want to be able to do is say, what if the people similar to the people who did take treatment but didn't take treatment had taken treatment? And that's exactly what inverse probability weighting does. It just counts the people who took treatment multiple times so that they count for themselves and the similar people. It's assuming that the people who didn't take treatment but were similar would have had similar outcomes had they taken treatment. Another way to think about this that may help no one in their intuition but may help someone is that you can think of inverse probability weighting as creating a pseudo population that has really nice property. In particular, if you weight everyone by 1 over their probability of receiving the treatment that they actually received, where here we use f of a given L. That's the probability that a equals 1 given L if a was 1, and it's the probability that a equals 0 given L if a was 0. It's just like your probability of receiving the treatment you did actually receive given your covariates. So if you weight everyone by that, you get a population that's like double the size of your original. You get basically the combination of the what if everyone had been untreated and the what if everyone had been treated populations. Here's the what if everyone had been untreated, and you have zeros for the treated branches. And here's that what if everyone had been treated, and you have zeros for the untreated branches. If you combine these, So there are no more zeros. This is what you get. And this pseudo population, which combines the treated and the untreated trees, has this really great property that the treatment is independent of the covariates. If treatment is independent of the covariates, then under exchangeability, you have no confounding. So association is causation in the pseudo population. In this population, you could just regress Y on A, adjusting for nothing, and get the effect of A on Y. That motivates an algorithm for how to estimate the average treatment effect using inverse probability of treatment weighting. In that toy example, there would be no reason to resort to a logistic regression model, or any model really, for the treatment probability given covariates. But let's say you don't have low dimensional categorical covariates. Let's say you have some continuous covariates or high dimensional covariates, like 10 of them, then you need a model. This first step would be to fit a logistic regression model for a probability of treatment given covariates. And then you could compute each subject's weight as 1 over their probability of receiving the treatment that they actually received, given their covariates. There are 2 options for the next step. One is to fit what's called a weighted regression model for Y given A, using the weights computed above. And this weighted regression corresponds to just regressing Y on A, not adjusting for anything in the pseudo population. So the weighted regression, like in the pseudo population, association is causation, but you can just do an unadjusted Y on A regression, just like in an RCT, if you want the effect of A on Y. Fitting a weighted regression of Y on A using the inverse probability weights that you just computed is the same thing as fitting just that unadjusted regression in the pseudo population. The way you would actually do this, like in R, if your data frame were called data and your outcome was called Y and your treatment is called A and your weights are called W, and you have a subject ID column called ID, then there are 2 ways you could do this. One is you could just do a linear model of Y on A and just add a weights equals W term. If you do that, then you have to use Bootstrap to get your standard errors. Another option is to use this thing called GEGLM. It's just another function. You regress Y on A. You set your weights equal to W. This is also going to demand that you tell it ID numbers for every subject that you have. And it also requires this extra argument, which we won't get into. But the reason you might choose to use this instead is because it also outputs a quick and conservative confidence interval without the need to do Bootstrap. So it's computationally easier. The confidence interval is guaranteed to be at least as wide as the true confidence interval that you'd get from doing Bootstrap. So it's not going to make you too confident in your results. It will slightly overstate your uncertainty. And in practice, a lot of people choose to do this instead of doing Bootstrap. But if you have the time and patience, Bootstrap is better. The other option that you have is, instead of fitting this weighted regression model, which is the unadjusted regression in the pseudo population, you could just do that procedure that we did on the trees. You just take each person, you take their outcome, you multiply it by the indicator of whether they took treatment little a. Let's say you want to know what would have happened if everyone had been treated. You take each person's outcome. You only count people who actually took treatment. That's what multiplying by the indicator for whether AI is 1 does. It just sets you to 0 if you didn't take the treatment we're interested in. And then you divide by the probability weight. This corresponds to going through that tree and only looking at the people who took the treatment that you're interested in, only looking at the treated branch, let's say, and multiplying by 1 over the probability of treatment for people in that branch to bring the people from the other branch over, right? To count them for both themselves and the people who had similar L's but who took another treatment. That's what dividing by treatment does. Then you sum up all those people and you take the average, and that's like the average outcome had everyone taken the treatment that you're interested in. And again, for either of these methods, you could get the correct confidence intervals via bootstrap. And if you want a conservative confidence interval, then you can use this approach, the weighted regression approach with GEE, GLM. And it's also computationally simpler because you don't need to do bootstrap. So this is inverse probability weighting for causal inference in a nutshell. I highly recommend reading chapter 12 and also the pages 20 to 24 of What If you want to build your intuition further.